Okay, I started the recording. Okay. Okay, now let's go through this. So you have seen the lecture 2, right?
Yes, sir.
Okay, perfect. Okay, now let's start with uh, some basic stuff. Uh, so let's call this thing relations on sets. So there is a textbook by it's a textbook called An Introduction to Mathematical Reasoning. Uh, and this is a good reference for this topic, but and I will go through the chapters of this book later, and I'm not doing it right now because this content is similar content is already been taught by Dr. Ramsingh. Okay, so I'll wait until he moves to actual analysis, and then whatever the left stuff that's left, I'll go through it. Okay, so but I'm gonna kind of uh, just give some definitions, and I'll do some things that are like just useful for us. Okay, but if you haven't seen these things before, and this is, I mean, you need to have like practice with these things, and we'll do that stuff later. Okay, good. So relation. So yeah, and uh, I have a Piazza post on this thing. Probably have seen that one too, right? So I'll go through it. So the relation on relation between two sets, A and B, is uh, is a subset of A times D. Okay, so the relation is nothing more than relation R. Call it R, and it's just a subset of A cross B. Okay, so and so in another, if you denote this set A element, I mean this is a picture for the finite case, right? And have all these points in the product set. Relation is just a subset. Okay, right? And uh, and typically, if you have a point AB in R, this is point AB, A comma B, and we write this thing as A R B. Okay. So typically ARB, yeah, that's that. Now, functions function is a relation R such that for every A in A, there exists a unique B in B such that A R B. Okay. So a picture is we are weaving for each simple A in here. You take A here, and now there are all the other points that sits above A, and there exists a unique element here that belongs to the relation. Okay, so it's not a subset that looks like this. Okay, for example, in here for this element, there's no element from the set B that sits above it. Okay, but for something like this, there are more than one. Okay, so if it is a function, it's going to be exactly one element. So it'll be like this. Okay, so this is your relation. And of course, you're familiar with this. But I mean, you're familiar with what a function is, but you haven't thought of functions as a special case of uh, relations, because you haven't seen relations properly. Okay, and now there are this actually more useful picture for a function. So this is the one that you have seen properly. This is your set A, and this is set B. We are saying like each element goes to some other element. Something like this. Okay. So this is a function. But if you put this, you cannot put this arrow. Okay, so that would mean that this element goes to two elements. Okay, so that would mean like, whatever that element is, there are two points in the relation. Okay, so this thing is not allowed. It's not allowed. And also you cannot have points like this. This is also not allowed. Okay, you cannot have points in the set A that's not that doesn't get mapped to the set B. Okay, good. Okay, now yeah, that's a function, and there are special types of functions. So say a function, say one-to-one functions. One-to-one functions means like this type of situations doesn't happen. So in here, what happens? You have two elements of A, of the set A, this one and this one. Both of them get mapped to the same place. So the one-to-one functions means like they don't cross. I mean, they can cross, but like they don't do this. Okay. So a definition would be definition. One-to-one function means if going from A to B is a function, and I mean in this case, if this is your relation R, and this unique element, we denote this by f of A. That's this B, we denote it by f of A. Okay, so in the case of a function, we use this notation. F is from A to B. Okay. So function F is 1 to 1. If we have f of A1 equals f of A2, this implies that A1 is actually equal to A2. Okay. And function is called onto. Onto functions means this thing doesn't happen. Okay. Meaning function for all b in capital B, there exists A in A such that f of A equals B. Okay, so any element, all the elements in the set B get mapped to by element from the set A. Okay, and bijection is a one-to-one. We write it like this: one-to-one and onto function. Okay, and if f going from A to B is a one-to-one and onto function, then there exists a function g from B to A such that uh, f of d of y, f of d of b equals b for all b in capital B, and g of f of A is equal to A. Okay. So a picture is, so if you have two two sets A and B, and you have this function f. Okay. Let me draw it like this. We have this setup. Kind of, you want to you go from here to here, but you want to define a function that's kind of undo the thing that f did. Okay, so that means you want to define a function that starts from here and go back here. Okay, now if you were to do that, first thing, if we have a situation like this, where this function is, if it's not one-to-one, we have two things going from here to this place, and now kind of to undo the what f did, we cannot I mean, if we were to define a g, then we had to define g of whatever this value to be equal to this and this, right? If the function is not one-to-one, when you try to define the inverse of the function, we can't do it because this thing is not going to be a function. Okay, so if you have if the function f is not 1 to 1, then you cannot do this. Okay, and similarly, now in the case of the function is not onto, that means there are points in the set B that are left out. Okay, so in that case, we have no idea where to map this thing. Okay, so that's why we require f to be a function that's 1 to 1 and onto. In that case, if it is 1 to 1 and onto, then we can define inverse. Okay, so that means this thing is not there, and everything goes into here nicely, and then we can define the function g this way. So we take this one, goes to here, and this goes to here. Okay. Yeah, so this would be g. And these formulas capture that yeah, if you start with any b from here and you map b using g, so that's g of b here. Okay, and then you apply f to this element, then you go back into here. Okay, that's what that means. And this condition means if you start with the element here and you map it with f, and then this is f of a, and then you apply g to that, you land back in the place you started with. Okay, now so we have this condition. This kind of looks interesting, and see, like we have seen the inverse of a group, inverse element of a group, and this one is actually kind of similar. Okay, so let's define. Let's get to that. So if you have definition, if is a function from a set A to B, and g is a function from set, let's say, B to C, and then you define f g composed f. Okay, so this one is a function going from A to C by g composed f of an element A is what you're going to do. You map this element A using f first, and now f of A is going to be an element in the set B. Now you can apply g to that. Okay, so a picture. So this is the set A, and this is the set B, and this is the set C, and this is F, and this is G. So this element A get mapped to this element B and then C. So the composition, call this thing the composition. It's gonna take the element A all the way to C. Okay. So I mean, we have seen this type of stuff. For example, when you have seen these things. For example, when you do chain rule. Right? So when you remember when you do this, like d by dx sine of x squared. Right? So what do? You differentiate sine. You have cos x squared times, then you differentiate x squared. That's 2x. Okay. So I mean, learn about it, whatever the way, but this thing is a composition of two functions. Okay, so the sin x squared is actually this one. So you have x. So x, you have the first function that takes x to x squared. So this is f of x equals x squared. And then you have the second function, g of x. So it's a g of y is equals sin y. Okay, y equals to sin y. Okay. So the proper format of the chain rule, if you write it correctly, so this is d by dx of g composed of f at point x. This is you differentiate g of f of x times f prime of x. Okay? So you have seen the idea, but probably not the notation. Okay? So you typically do it with I don't know, you put a variable u, this thing to be u. So u equals x squared, that's the first function. Okay? Good? So that's a chain rule. Okay. Anyway, so you have seen this thing before. Now let's have a look at this thing, because this thing looked very that thing looked very familiar. Okay. So let's look at this one again. See another look at another look at this. Okay, so in write something in this case. G is called the inverse of f, and we write it in this way. You write G to be f minus 1. Okay, and yeah, I mean this thing like kind of screams groups. Okay, because why are you using this notation, right? And so let's look at G equals F inverse. So this is your set A, and now F is a map going from here to here, B. And then G is a map that goes from here to here. Okay. Now, if we take G composed F, G composed F, that's a map. So you're applying F first, right? And so G composed F is a map that goes from A back into A, right? Yeah. So that's a map like this. Starts with A and then ends with A. And similarly, F composed with G, that one starts with B, starts with the set B, because G is the domain of G. So this one is called the domain, and the other one is called the codomain. The starting place is the domain. So G composed F, that's going to go from B to B. Okay, so that's a function like this. Okay. Now, so in A, there is a function that's called the identity function. Identity function on A, which is the function that doesn't do anything, meaning that ID A of X equals X. It's a function from A to A, which is just the identity. And in here also we have identity function in P, and the identity function in P is defined in this way. Okay, so the that condition that we had in here, this condition right here, this one, we can write it in this way. So this one is, first one is telling me that F composed with G, this function is the function that assigns B to B. Right? So this is the identity on the set B. And this is telling me that this is G composed F, and this is the same as identity on the set A. Okay, you remember in the case of inverse, like in groups, inverse of element is another element. When you multiply, you get the identity. Right? So now we don't have the multiplication. The problem is this composition looks like sort of multiplication, but when you do this composition, like you get say like in here, so if you compose f and g, you ended up in here, function going from A to A. In here, you get a function going from B to B. Okay, so these two are like, you cannot make them equal unless the set A equals set B. Okay? Good? Okay, now. So let me give you the exercise. So the exercise 1. Let capital A let capital A be a set. So let capital A be a set. And let G be the set of functions from A to A that are bijection. Okay. Show that this set G together with composition is a group. Okay. So that would kind of clarify the problem we had. Okay, so because this looked like something is happening that's similar to have all the inverses and looks like it's a group. This connects it. Okay. Now, there's much more to be done with these one-to-one and onto functions, and I'll get to it. I'll do complete probably like a half a lecture, like probably 2 hours, that maybe a full lecture. Yeah, there's good theorems here. Uh, for example, this is a very difficult theorem, but so think about this. Uh, if f is a function from a to b, if this function is one-to-one, also there exists both one-to-one. It looks like we have function here, one-to-one, and it might miss some points. Okay, we are not given that this function f is onto. Okay, but it's one-to-one. And also, but there's a way to come back from B to A. It is also one-to-one. Okay, so this function G is also one-to-one, and there might be points that are missing here. We have this setup, then there exists a function h going from A to B. Bijection. There exists h bijection. Okay. Somehow, like you can. Okay, it makes sense, but this is a big theorem. Okay, so this is called the Scholder-Bernstein theorem. So there's lot left to be done with the one-to-one and onto functions. Okay, now next thing is I'll talk a little bit about uh, equivalent relations. Let me. So yeah, so this is equivalent. So you consider consider this setup. Consider this setup. We have function f going from A to B, and this function is onto. Okay. Now here is the exercise. Consider the sets consider the collection a collection of sets. Let me call it we call it PB. Okay? These are all the elements from A such that f of A equals B. Okay? Show that PB intersect with PB prime equals they're like equals empty set if B not equal to B prime. They're pairwise disjoint. Okay, and if you take all the union B over capital B of PB, you'll always get the whole set A. Okay, a collection. So here is a picture. So let me draw it this way. So this is my set A, and this is my set B. Capital B. Let's say everything in here get mapped to this. Okay, and so on. So everything in here, it's mapped to here. So every time we have a onto map, if you look at the pre-images, those pre-images, so this is B, and this set is called F inverse B. That's also denoted by PB. F inverse B. So even though I use the notation F inverse, I'm not assuming that F is invertible. Okay? So that's why I use the PB. But the point is, like, this type of sets actually break the set A into pieces. And it's like it's a different kind of breaking, because the union of all these things equals to A, but those each individual parts, they're pairwise disjoint. Okay, so what we are seeing here, this is same this type of this setup. This is called a partition. Okay, so a collection of sets like this, PB, B in B is called a partition. Okay. So the okay, and then so we have like three different notions. So we have the so like around this idea of partition, we have actually three different concepts, but they're equivalent. Okay, so the first one is the idea of a partition, and now let's define. So like onto function, and if you have function like this, and then you get a partition. If you have a partition, you can create a onto function. Okay, so you define the set B to be partitions. right? And then, the elements in the partition, you map it to the partition. Okay. And so you see the onto functions are the same as partitions. And then the last concept is we can if you have a partition, we can define a special type of relation. So let me call it E alpha in some set be a partition of A. This means two things. Union alpha, take the union alpha in here of E alpha. This is going to be equal to the whole set. And the other one is E alpha intersect with E alpha prime is equal to empty set if alpha is not equal to alpha prime. Okay, so that's a definition of a partition. So if you have a partition, from a partition you can define a relation. Consider the relation we call it A relation on A. Okay, so in set A we define a relation where ARP is if and only if A and B are in the same partition, same E alpha. Okay, so we define this thing to be A is related to B if this happens. Okay. Now this relation, say like we're trying to describe this partition situation in terms of a relation. And this relation has these three properties. Note that A is related to A because A and A are in the same E alpha. Okay. If A are B, then B are A. If A and B are in the same partition, then B and A are in the same partition. Okay. And third one is ARP and BRA implies BRC implies ARC. This is telling you like if A and B are in the same E alpha and then B and C are in the same E alpha, then A and C are in the same E alpha. Okay. Good. So we have like three different concepts, different ways of looking at the same thing, same picture. Okay, and then you can go back and forth between those. Okay, good. And this type of now the definition. So let me call this thing condition 1, 2, 3. Condition 1, condition 2, and condition 3. So we have definition of an equivalent relation. So the equivalent relation R on A, we call we have a relation R on A, and we call that relation R is equivalent relation if it satisfies these three conditions. Okay, and again, so here is exercise. Exercise 3. So let R be an equivalent relation on A. We denote it by this guy, A square bracket. These are all the B's in R such that A is related to B. Okay, and consider these things, show that these guys is a partition of A. So it's like in here, we had a partition and we construct a relation by looking at the partition, and you can go back. Okay. And this is kind of the way we we take care of this partition situation with the equivalent relations. Now, the last one. So this is the third topic. So equivalent relations and partitions and quotient. Quotients. All three things are the same. Okay, so the quotient is in this setup, exercise 4. This is the follow-up to the exercise 3. Follow-up to exercise 3. We consider this map F. So we consider the set B, which is the set of equivalent classes. So this guy is this thing is called an equivalent class. Okay, and we consider this set B. This is a set of equivalent classes, and then you have the quotient map. We have a map. We call it pi, going from A to set B. And we denote the set B by A divided by this relation R. So that's the relation R. Typically, like we don't use the letter R, we use something like the common notation is A related to B. Okay. And yeah, and this map is pi of A is given by this. And this map is always onto. Right, so you have the same they have like same three concepts, but they are essentially doing the same thing. You have onto map. If you have onto map and you look at the pre-images of elements that form a partition. If you have partition, then you can define equivalent relation. And if you have equivalent relation, you get partition. And so on and so on. Okay. They are like three different concepts, but they do the same thing. Okay. Now, let's go to the show that this is onto. Yeah, let's not keep this thing exercise. There's nothing to like no. This is just telling you if you have an equivalent relation, you get onto map. Okay, always there exists onto map. And again, there are more stuff to be done in here. Okay, and now the next topic is there's another type of relation. This guy's partial orders. So what's happening in there? So like these are like the like in like 3 less than 4. Like this less than symbol, that's also it's basically like you say that it's a relation, two elements, right? So this is a special case of a relation. Okay, so a relation R on a set A is called a partial order if we have these three properties. The first one, ARA, okay, it's like, think of this as less than or equal. Okay. And then the second property is ARB and BRA. This implies A equals B. Okay, so this property is called reflexivity. Reflexive means like you can flip and you get the same thing. And this property is called symmetric. Right? If you have A and B, and then you have B and A. Okay, but in here, this is called antisymmetry. Okay, and we want this thing for a relation like less than or equal. Can't have like A less than or equal to B and then B less than or equal to A without being A equals to B. Okay, and then you have third one is A less than B and B less than C. This will imply A less than C. So this is transitivity. Okay, so the partial orders and equivalent relations are differed only by this property. Okay, but they describe like totally different structures. Okay, now, so let's go and give a like really good example. So example. Okay, so let's start with the really bad one, a really easy one. So that's like let's say integers and less than or equal. This would be a partial order. Okay, and another example, take any set A, and then you consider P of A. This is the subsets. Let's say P is a subset of A. And in here you can now you consider this set, the set of subsets, and you take the relation to be this subset. Okay, and this is a good exercise. Show that exercise 4. Show that this thing is a partial order. Okay. Now, okay, here is the good example. So consider set A to be all the points and lines and planes. Okay, in R3, for example, in space. And then you define A and this element of. Okay, so if the point is in the line, then we call that thing is like, for example, if you have this line L, you have point A and point B here, we say A is not related to B, L, but A is related to L. Sorry, B is related to L. Okay, so this belongs to symbol that can be used to get a it can be used uh, as a relation. Okay, and if you think about this thing a little bit carefully, this is a special case of the this is like a special I mean that this C and B are related, and we are not looking at all the subset. Like if you think about the space, and you are not looking at all the subset, but you're only looking at subsets that are of the form planes, lines, and points. Okay, and yeah, good. And you can show that this is a partial order too. Uh, I think it's better to use the subset. So because when you have line and a plane. You typically don't write the line is an element of the plane. Okay, so in here, what I'm doing, I'm using kind of abusing in the sense that I replace the point with the set with the point. Okay, so we typically write the point is in the line, and this one set that contains the point is a subset of the line. Okay, but there's like tiny bit, but this is something really 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 powerful. Okay, and so when you think about uh, geometry, okay, and we draw pictures and you draw triangles and this and that, okay, and but this will give you a kind of I mean, if you follow this path, the geometry has a partial order with like bunch of other properties that allows us to like detach ourselves from the pictures. Okay. Okay. This is huge. And now think about this. Even if all the things we did with the pictures, what if you set up the uh, axioms for this partial order right, and you can have the picture on the side, but all the proofs that we're doing are going to be just following the rules of the partial order, the special type of partial order. We need to add more axioms to the partial order. What if that is the case? Okay. Now what if we can define what a geometry is in following this path? Actually, so we will exactly do that. So later we'll give a definition of a geometry. Okay. And actually there is a saying, so we have algebra and geometry. And like, back in the days, it was people would do algebra and some people would do geometry. And but nowadays, like asking whether you want to do algebra or whether, asking whether you want to be a geometer or whether you want to be a algebraist is like asking whether you want to be blind or whether you want to be deaf. Okay, so they are like very, very, very like very related, and we'll prove a theorem, and it'll take a couple of days, and I'll prove this theorem. Okay, so I mean it'll take a while to get to the definition of the geometry, and then there is something else. So okay, I started this. So we have these things like the congruent triangles and various theorems about triangles and this and that. Okay, so this is high school, and we deal with the pictures. Okay, and and uh, and then you have these are like lines and points and planes and everything, right? And then you have the idea of partial order. Maybe what's happening is not the pictures, but like have partial order, that partial order, and we have like more properties. Okay, so and then there's the third picture. This is coordinate geometry. So in the coordinate geometry, we have lines and points and planes and all that, but they're described by equations, right? So that means we have like, if I draw a line here, right? I draw a line here, and you're kind of thinking that maybe that line is like this. Like the lines that you drew in high school. Like, okay, if you have a line in the high school, like geometry book, like a long line, what do you think of it? Is that like what's the difference between that line and the real line?
We can show the line with the equation. This
Yeah, so the line with the equation is in here, right? And then you draw lines in high school, like these triangles, but you know that you can extend it, right? So intuitively you think like this line is same as the real line, like this one. Okay, we can rotate this and put it in here. Okay, can move it like do a rigid motion and put it there. Right? Now, the thing is, this thing has to go. This picture stuff has to go. Okay, I mean we will use pictures. Pictures are very important, but like when you try to define it formally, the picture's gonna go away. Okay, and you'll define a geometry in here. So you'll give the definition of a geometry in here, right? And then you'll show. Uh, okay, so give me a second. So like we have what we have done in here, the example C, we have shown that these are like all the points, lines, and planes in. I didn't say like I say a space, but what you really doing, you're thinking in terms of the coordinates in here, right? So these are like the lines and planes and points in the coordinate geometry. Those will form a partial order, right? So it's easy to go from here to here. Okay, but how about this way? If you start with some partial order with like bunch of properties, uh, can you show that whatever the stuff that we have is actually like some bunch of stuff from a coordinate geometry? And there is a theorem, and that theorem is called the fundamental theorem of axiomatic geometry. That's the coordination theorem. See, like in A levels, you have O level stuff in here, high school stuff, and you have this stuff. If you think about it carefully, they're separate. They don't talk to each other. Right? You build up the connection that this line is like this line. Lines are lines and the real line. Okay. So there is a theorem that you will prove that tells you if you start with a partial order, from this you can construct algebraic object that looks like reals. That's called like real numbers is a field, but what you get is something that's weaker than a field. It's called a skew field or like a division ring. Division ring is a ring where every non-zero element has inverse, but it doesn't have to be commutative. Okay, so you'll prove that theorem. That's going to be like real fun, and so we're gonna work towards that too. Okay, now where are we at? Okay, now, yeah, let me talk about this thing, and then, so I have something. There is something. Like while we're at it, I was originally planning to do the little bit more linear algebra stuff and come back to this, but I think it's good to just Arnid. Okay, so let's start. So let me do this like it's a very simple thing, but get this thing started. So uh, so we can do addition. So the point is to kind of so going from here to here, that's easy. Hmm?
So I can see the screen.
Oh, okay, okay. So going from here to here is easy, right? If you have planes and everything in coordinate geometry, and then you can uh, verify something like that would satisfy uh, axioms that relates to partial orders and more. Okay, but going from here to here is difficult. Okay, so like going from here to here means like you have to kind of construct something that look like a line. Okay, so if you have one line, then you have three of them, and then you have coordinate system, and then you can write equations to describe lines. Okay, so let me write these two things. So from geometry to algebra. So I'm gonna do something that's uh, really interesting. So you take a line and you mark, you pick a point, and then you call that the zero. Okay, and then you mark a point and you call that this is A. And let's say you can use lines to add, let's call it add A. Okay, so you want it to be add A applied to B should give you A plus B. Okay, so if you take a point B here, so you want to kind of construct this point right here. It's called A plus B. You want to do it using the lines and the planes. Lines like the in the sense like the axiomatic geometry. Like, okay, so there is one way of doing it, which is this. You pick uh, parallel lines like this. Okay, and then through O and B, and you pick two parallel lines from that goes through A. Okay. So if you have this set up, see the point is, so this length OB, this length OB is going to be equal to this length of these parallel lines, and that length is going to be equal to this. Okay, so you can use the parallel lines to get to here. So this is your point A plus B. So what you're doing, we define the addition by using this type of construction. Okay, and you can I mean, this construction, we pick these blue lines and the green lines, and you can show that this point right here, this point here is independent of the choice of these blue lines and green lines. Like if you pick like two different, like another pair of blue lines here and then another pair of green lines, you would get the same answer. So it looks like we define this addition using within these lines, but it's not. Okay. And the kind of the real like once you define this geometry, and so we have this picture stuff when you move it to here, and then we'll be able to do this construction. I mean, we'll look at the picture, but you can carry it out just using the partial loader. Like from the partial loader, we'll define the addition. So you're really going from here to constructing this line. Okay. Now let me tell you like how the multiplication. I mean, again, like I will go through these things in great detail later. But this is the kind of the beginning. So with multiplication, again, we have the same setup. Have 0, 1, B, A. Okay, so the what we have, if we have this so if we have two parallel lines that go from 1 and B, and let's say we have another line going like this. So if these are parallel, so in the ratio of these two is like 1 to B, right? And so that means the ratio between this is 1 to B, because these lines are parallel. Antakan for me, okay? And now we draw another two lines going from here and going from here. So now the ratio between these two, know that this is 1 to B. If that is 1 to B, then if this is A, then this length. So if this is A, and then this length is AB. Okay, so you can use the parallel lines to actually define the product. Okay, and you will carry this thing out in the setup of you will define what a geometry is and go through this. Okay. Now, so I'll postpone this thing for now, and I'm gonna, I mean I will go through other stuff, but I'll come back to this theme. Okay, going from like this connection between algebra and geometry, and this would be like the kind of the step 0, like seeing that you can use parallel lines and stuff to define addition and multiplication. And you want to, at this step, you want to convince yourself, even though we did this thing using this picking up these parallel lines, the final result is actually independent of the lines we picked. Okay. Now, so let's go back. Now, So let's switch gears and let's go back into the go back to the. So let's go back into the linear algebra part. Okay. Group actions on a set. So last time we were here. So we did something, define elementary operations. And we showed that these things can be done by elementary matrices. Okay. And then we showed that we constructed this group G. These are products of E1 up to Ek, where each I is an elementary matrix. Okay. Now, we showed that this is a group. G is a group. And we showed that G is inside GLN. GLN is all the matrices, n by n matrices over field A over F, and where A is invertible. Okay, so we did so we done with this. Okay, now so let's do the second part. Now we have been let's look at the systems. We have like studied this thing earlier, but now we can do it in a little bit more detail. So we have systems, m by n systems. Okay, so they look like this. So this is X, this is B, and this is my matrix A. Okay, and we have the m by n systems. They can be written this way. Okay, so this is A. It's m by n matrix. Now, so when you do row operations, so we do row operations. We do row operations to the matrix A. Okay, and so we want to look at what happens in the setup in a little bit more detail. Okay, so we define this thing. So define, say A is similar to A is equivalent to B, called row equivalent. If we can get B from applying row operations to A. Row operations finitely many. Okay, finitely many row operations to A. Okay, so in other words, the matrix B is going to be equal to, take matrix A and then you apply bunch of row operations E1, E2, dot 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 ek. Okay. So what you're really doing, we have this set m by n matrices, and you define this relation. We say A is related to B if you can get to B by applying row operations to A. Okay. So what do you think happens here? What type of relation is this? So position, this thing is an equivalent relation. Okay. So to prove this thing, the first thing you had to show that A is related to A, right? So this is the reflexivity. You can write A to be identity times A. And you know that the identity matrix, which is m by n, m by m, this is a row operation. It doesn't do anything, but it's like you can think of it as scalar multiplication, multiplying a row by a scalar, but the scalar is 1. Okay, so we can get to A by applying a row operation to A. So the A, we have this. Now, if we can go from A to B, then you can write B as in this way, ek dot 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 E2, E1 of A. If you can go from A to B, then you should be able to go to B from B to A, right? In here, you can write A as B, you multiply by ek inverse dot 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 E2 inverse and E1 inverse. And all these inverses of elementary matrices are also elementary matrices. So this will tell you actually B is related to A. Okay, so this relation row equivalence is symmetric. Okay. Now the third property is if A is equivalent to B and B is equivalent to C, you want to show that A is equivalent to C. Okay, so since A is equivalent to B, you can write B as E1 dot 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 ek, and then since B is equivalent to C, you can get to C by, let's say, E1 prime, E2 prime dot 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 E k prime prime applied to matrix B. Okay, so that means this is same as E k prime prime dot 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 E2 prime E1 prime, but B is ek E1 Right now we have written C is a bunch of elementary matrices time A. That means you can go from A to C by applying elementary row operation. Okay, so that means C is related to A. Okay, good. So that means you have this nice picture. So if you have this equivalent relation, that means you have partition. Okay. Okay. So now all the matrices, M by N matrices, they actually belongs to like separate blocks, and they don't interact. Okay. Good. Now, but we can say more. For example, typically when you have a partition, this piece is big and this piece is, small. Right? We don't have, we don't get like more information out of this. We don't see how these two relates. Okay. So, good, but this picture is what you get when you prove that the row equivalence is a equivalent relation. Okay, so the matrices are like, yeah, you get this picture. Partition. Now, let's the structure that you have here is actually finer than what you have in the picture of a partition. Okay. Now, so let's call this thing. So the next part. This is like 2 point A, 2 point B. Is we have the group G. G is the finite products of elementary operations, and we have shown that that's a group. Okay, and then you have this set. These are M by N matrices with entries from the set F. Okay, so we have this definition. I mean, the structure that we have here is actually kind of is more detailed than the picture of a partition. To understand that, what's happening is we have a group action on a set. So the group action on a set is a map from G cross some set into that set. Okay, so that means write this thing G dot S. So it's not quite a binary operation, because for a binary operation on a set, you have the same set. But in here, the S doesn't have any structure, it's just a set. But G has the group operation. Okay, so let me call this thing M. Okay, so M G comma S, and this is element in S. We typically write this thing as write this thing as G dot S. Okay, and then you have properties. So if you multiply by the identity element, then you get S. So E is the identity. Okay, and then the second property is if you multiply G1 times G2, G1, G2. This is same as G1 okay. So these are the two properties. Now let's see. Now we'll show that so this map the exercise 5 show that row operations is a group action. That's it. More precisely, we typically write the group G act on the set S. So in this case, our group have the same group G here, and this act on the M by N matrix. Okay. Good. So, and it's easy to verify these things. Now the picture is this. So if this is your set S, so this is your element S, and then you apply G, and then you get G dot S. Yeah. Okay. And now so I have the definition. Let G act on S be a group action. For some element S in S, the orbit of S is given by okay. So the picture here is let's say this is element S, and all the things that can be obtained by multiplying by G. So this, all these things are, this is called the orbit of S. Okay. So this would give you a better picture than the one that we had earlier. Right, so so in here you can show that exercise here, exercise 6, show that orbits form partition of the set S. Okay. So in this case, the picture that we have here is picture that we have is actually very that's kind of nice. So this is our matrices n by n. Okay. And what we have here kind of like a bundle of sticks. Okay, and then each stick is same as the group G. It's not exactly equal to G, but it looks like the group G. Okay, so good. So So what I mean is this. If S1 is not equal to S2, right? If you have two, like S1 here and S2 here, then there exists a bijection F from S1 to S2. Bijection. There exists. Okay. So if you have two of these orbits and they are in one-to-one correspondence, because you can map S1 to S2, an element in the orbit that's like G times S1 that can be mapped to G times S2. Okay, and it's not that there is something that's going on a little bit, so you might want to look up this thing. Free actions. So what's going to happen actually? This action is like when you multiply by the group element. If the group element is not the identity, then that's going to move you away from the starting point. Sometimes you can have a group action where you multiply by the group element, it doesn't move. Okay, so the free means that, and you need that to prove this thing. And it is easy to prove that this action is actually free action. Okay, but now the point is like you're getting like something really, like the picture is going to be like, it's like really nice. Okay, now, so what we have, let me draw the final picture. So we have this. These are my matrices. Right, and each we have these orbits, and each of these orbits are, so if we take a element A here, and you have the row reduced echelon form of A. Okay, so we have this is the quotient map. We have the set and you have these partitions, and then each set, each orbit can get mapped to a kind of the equivalent class of that element. But in our case, the equivalent class can be denoted by the special element. There's one like unique element in there. Okay. So this is the nice picture, and each of these things are called fibers. So these guys are fibers. It's similar to G. Okay, and this is the kind of the picture of the the picture of the systems, M/N systems. Okay. Now let's go back. Go back again to so we're done with the group actions, and we showed that this is what's happening in when you do row reduction and something like this. Okay. Now, let's go back. Let's go back again into the this is part C. That's 2.C, 2B, and then 2C. So this is, let's go back into the systems of linear equations. Okay. So right now you can define, define the row, reduced row echelon form. Okay, so the definition is you have yeah, so this is let's say this is R. It's a matrix M by N. See, like last time when I talked about this, I didn't mention it. Because I didn't have the notation. So this thing has four properties. The first one, so all the rows containing only zeros appear at the bottom of the matrix. Okay, and then second condition. So in any non-zero row, the first non-zero entry is 1. The next one is for any two consecutive rows. The leading so this one is called the leading entry. Sometimes you call that the pivot. The leading entry. The lower row is to the left of to the right of the leading entry of the upper row. any column that contains a leading contains a leading entry has zeros in all other positions. So let's draw a picture. Okay, so if we have rows that are all zeros, they are going to be in the bottom. Okay, so we have this guy is all zeros. And then if we have a row that's not all zeros, then that row looks like this. A bunch of zeros, the first non-zero entry is 1. Okay, and then you can have 2, 3. Right? And the third one tells you for any 2 consecutive rows, the leading row. So if you have this one and this one, let's say you have something like this. And this is another non-zero row. Something like this. And this is telling you that this is not allowed. Cannot have this way. So the leading entry of the upper row has to be in the left. So that should be something like this. See 1 here and something like this 2. Okay. And the last one is if you have a pivot, like if you have a leading entry like this, and everything above that has to be all zeros. It should be 0. Okay. Typically, you remember it this way, kind of like a. Okay. And we kind of, earlier we did example saying that, when you actually solve the equations, you can get into situations like this. Okay, and we have the homework problem to kind of write you this. Ask you to write the algorithm to get any m by n system into this format. But still, when I looked at the solution, they're not that good. So you actually write the solution assuming that the matrix is in the perfect setup. So I think what you should do, you have the algorithm and then you kind of plug in some test cases and then see how the algorithm would perform. Right. So I have given you the bunch of examples, and then you can take that example and try to follow your steps exactly, and then you see that it doesn't work. Okay, so that's it, but it's doable. But this is the form that we're after now. So the proposition a matrix A in here by is row equivalent to 1 and only 1. Matrix R that has row, reduced row echelon form. Okay. And so let's make this thing again the exercise. I know that I asked this one earlier too, but let's make this thing exercise 8. Because we have had only one part. Okay. So you have shown that you can get into 1, but this is asking you also that so you can get to exactly 1. Good. Now, and then when you can do it, you have started the matrix A, and then this is telling you that you have unique row reduced echelon form. So that means you can define this map RREF. You can think of this as a function from m by n matrices to to the, let me call it so the matrices that are in this format. Okay. I mean, this one is actually a command in MATLAB or something. Okay, so we have, in this case, we write R as the reduced row echelon form of a matrix A. Okay, and note that in this case, because you can get to A from R, so write it. We have this one. Okay, you can start with R and apply these things and go back to A. Okay, now we have like some important theorems, and so call this thing theorem. A matrix in here. This matrix is invertible if and only if the reduced row echelon form of the matrix A is the identity. So all the invertible matrices have the, okay. So in this picture, in other words, all the invertible matrices are going to be in one of these fibers. Okay. And pro. So you have two directions. The first one is if A is invertible, then you want to show that the row reduced echelon form of A is identity. And then the other direction is if the other direction is easy. So let's start with that. So assume reduced row echelon form of the matrix A is identity, and you want to show that the matrix A is invertible. Okay, if the reduced row echelon form is of A is identity, then you can write A as E1, E2, dot ek times the reduced row echelon form of the matrix A, that is in this case is identity. Okay, and now this matrix is invertible. Okay, so from here, I mean we have shown this thing earlier too, because this one, the product in the right hand side, this is an element in the group G, and we have shown that it's a group. And okay, now let me write it this way too. So this is same as A. We keep multiplying this thing, so we have E1 inverse, E2 inverse, all the way up to EK inverse. This is going to be equal to A. We keep multiplying from this way, EK inverse, dot E2 inverse, E1 inverse, right. Okay, so this is the definition of the inverse. Okay, so that direction is easy. Now let's prove this one. So for that we assume capital A is invertible. Okay, so that means the Rx is some matrix B, invertible matrix. Invertible matrices are denoted by GLNF, such that let's not use this notation. If A is invertible, then there exists another matrix in here, and then of F, such that AB equals BA is equal identity, right? Now you want to use this data to prove that the reduced row echelon form of matrix A is actually identity. Okay. Now, so let A be equal to E1 up to EK times R. Okay, so this is in the that's a reduced row echelon form of the matrix A. Now, this, let me find that. This is plain. Exercise. Exercise 9. Let R be reduced row R be a matrix in the reduced row echelon form. This is actually n by n matrix. Okay, n by n. Then R, it is not equal to the identity. This is same as if and only if last row all zeros. So one direction is easy. If it is last row is all zeros, then it is not the identity matrix. But if it is not the identity matrix, then the last the last row has to be all zeros. See the so assume that like the it boils down to whenever you have a pivot, this length is bigger than this length. This length is larger. Okay, because the because you'd be dealing with things like this. So at each step that you go down, you will have one or more going this way. Okay, so if you play with this, you can prove this. Okay, and okay. So now with this, so you assume this, and then you go back here. Now, so you want to show that the you want to show that the R is equal to IN. So we need to show. So we need to show that R is equal to identity. Okay. If R is not equal to identity, then from the claim we know that the bottom row is going to be all zeros. And bottom row of R is all zeros. Okay. So what you ended up having, and you want to get a contradiction. So let's look at this. Something like this equation. Right? So we have A to be this, and then so we get A B equals IN, but A is equal to E1 dot 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 En equals times RB, because this is your A equals identity, right? And then then you can move this E1 into this side, right hand side, and you bring it back to the other side. So we get R B E1 E2 dot dot En equals In, because we can bring this E1 multiply by E1 inverse from the right hand side, from the left hand side, and then you get E1 inverse here, and then you multiply from this side, right hand side, with E1. So then you cancel that one, you get the E1 into here. Okay. So now, if you look at this, when you multiply with this one has all zeros at the bottom. And if you have all zeros and you multiply by this matrix, then this one will have zeros at the bottom, right? And if you have a matrix that has zeros in the bottom, then you multiply by that, you will get zeros in the bottom. Okay, so this would imply that you'll get a matrix with zeros in the bottom, and that would equal to identity. So this is a contradiction. Okay, so that means the reduced row echelon form of A, which is equal to R, that should be identity. Okay, so this completes the proof. This is actually pretty good. So you have shown that the matrix is invertible, then the reduced row echelon form is equal to identity, right? But again, if the reduced row echelon form is equal to identity, that means A is going to be of this format. Okay, but a matrix of this format is actually an element of the group G. Okay, so once you have this theorem, it follows that if you have an invertible matrix, that invertible matrix, let's call it A, can be written as a finite product of elementary matrices. Right, so this was the thing that we wanted to prove. Right, so earlier we knew that the G is a subset of the invertible matrices, but now we can show that invertible matrices are subset of G. Okay, so let me write this thing as a corollary, but it's easy. So the corollary, we have invertible matrices. This is actually equal to G. Okay. Let me give this thing as exercise 2, but it's easy. Exercise 10. Good. So any invertible matrix can be written as a finite product of elementary matrices. So let me finish this one too. It'll take, this is a very interesting one. So if you have two matrices, A and B, and their product is identity. Okay. But can we tell from this that A is B inverse? We cannot, right? We have to have the other side too. Not A times B, but also B times A also has to be equal to identity. Right? But this proposition tells you that if you have this, such that then we have BA equals identity. And again, this holds for matrices, but it doesn't hold for like general groups. Okay, you can have examples where you have one-sided inverse, not the other side. Okay. Now, so let R be equal to the in other words, we write A as so then we can write E1 dot EK R B equals identity, and the we can do the same trick as before. So we can write R B E1 dot EK equals identity, right? And this will tell you that this guy must be equal to identity. If it is not equal to identity, then it will have bottom row 0, and then you, right? So as before. So this thing would give you R equals identity. So once you have this, so actually A is this one, E1 dot EK, and R is identity. Now if that is the case, so AB is equal to E1 up to EK, B equals identity. And then you can play with this equation again, multiply by E1 inverse, and then multiply from the other side. So you get B times E1. So in other words, B times A is also equal to identity. Okay. So most of the work for the systems of linear equations are done at this point, but we have to go through the homework. Okay, that homework with the developing the algorithm and showing that it always leads to a unique row reduced echelon form. That's the thing that's left. And so, and yeah, and then you can, like, solving the systems, you apply the, so we know it from the kind of theoretical point of view, but also we know that this algorithm works. And then you need to classify kind of types of the solutions. That's actually for that you have to, like, look at the right hand side. The equation in the left hand side, you get to the echelon form, and then you look at the right hand side. For example, if the bottom row is 0, but in the right hand side you have 1, then there's no solutions, right? And so on. So there's like tiny bit of left, but yeah, those things actually can be done in homework. Yeah, I think that's that kind of can call that's the end of the introduction. So this is the end, the introduction. So what we did, basically, we used systems, M by N systems, and row operations. And N by N systems, row operations, and matrices to introduce basic algebraic structures. Right, and at the same time, we kind of solved, kind of analyzed what's going to happen to the M by N systems, like, fully. Now, at this point, there's two things that I can do. Next steps. So one thing is to go over the linear algebra done right book, and you will just go through it quickly. And the other one is to go a little bit into each of the topics, like groups, rings, modules, and fields, and stuff, algebras. And then, like, you kind of take the abstract algebra book, and then you go through section 1 of each of the chapters. In that way, you have basic examples and, a couple theorems. And so go over basic algebraic structures. Like section 1. Section 1 on each chapter. You do that, and then you come to the linear algebra done right book. So what do you want to do? 1 or 2? This or this?
I think second option
Is
uh,
better?
yes.
Okay, let's do the second one. I like that one too. Okay, so nice. So in that way, like, I mean, so when you prove basic properties of vector spaces, you can say like, oh, this is a group, and you prove this for a group, right? Otherwise, the vector space has a lot of, like, huge list of structures, huge list of, like, properties, but if you think of it properly, and there are like substructures and so on. So I prefer going over the each chapter, like the section 1 of the chapter, basic definitions and examples and basic properties, and you will get the practice of like what kind of little tricks you have for the each type. Good. So any other questions?
No, sir.
Okay, so let me stay for a little bit. Let me turn off the sharing and the recording.